Any more questions for Professor Nanda? Let's once again. Oh, yeah, sure. Sorry.
So, this is all from the point of view of probabilists, okay? But suppose I'm talking about the physicists who talk about randomness or chaos in the system. They have other ways of defining randomness and chaos in the system. How this, it seems that the development seems to be divergent, right? This entropy development in probability and those who try to give a mathematical modeling for randomness or chaos in the system. There seems to be a completely parallel and divergent development. So, is there a way to connect the two? And then this issue of postulates is probably solved. If you think about the physicist problem, that's motivated from some physical phenomenon and based on some experimental data. So maybe the postulates should be formulated from those problems, not in abstract, like the way the probabilists are trying to do. Okay.
I can tell you one thing that I really don't have much idea about physical problems as such, how physicists do. But a couple of research papers I have reviewed for American Mathematical Review regarding entropy. And there what I have seen that there eventually the definition of entropy is exactly the same. Their method of your physics and how they interpret it, that is different. But the definition is exactly sigma.
I'm just talking about the definition of entropy. Okay? They have different, see the basic purpose of entropy was to measure sort of the amount of uncertainty or randomness in the system. Okay? And then people have come up with different concepts that have different names than entropy. Okay, but the basic objective is probably the same. When they define this notion of chaos and they talk about the various indices related to chaos, the basic objective is same. Okay, so you're trying to measure something like the amount of randomness or uncertainty in the system. Okay. So I think this issue of postulate should be related to that. What exactly you're trying to do. I think if you try to get sort of mathematical consistency, then like some of the questions that you pose, those are very valid questions, and you end up getting negative entropy. What are you going to do with that? And when you are just having a linear transformation, the entropy should remain same, and it's not remaining same. But I think the basic issue is that what do you want to do with the entropy, and what is it that it's trying to measure?
We are using entropy in a reliability as such, and there also we are trying to find out this uncertainty. But one thing actually I will differ in this way, that some people call it a measure of randomness. I have really some reservation in that. I would like to tell you measure of uncertainty, but not really measure of randomness, because as far as I feel that it measures uncertainty, not the randomness. Because the thing is that if I have something uncertain, this need not be random, because there need not be anything what is random or stochastic. The thing is fixed, I don't know. But that way, calling this something random.
Entropy not measuring the randomness, it is measuring some other type of uncertainty. That's what I am not able to perceive. Not able to
No, randomness thing is that suppose tomorrow will be rainy day or sunny day, I don't know it. Or maybe anything different, right? And as far as this physics is concerned, physics is the same thing. Physics behind this entropy is same thing. Only thing is that I have seen some chemistry problem as well. That if you have some chemical problem, there you have to find out your probabilities properly and use Shannon entropy. That is perfectly fine. I don't see any class as such. But the thing is, recently I was trying to write one review paper on entropy starting from 1948 to all the way up to 2018. And what I could see that what you are telling is correct, it is really divergent in the sense that I have taken a very narrow path and only I could review this part. Because if I consider this everything, just review itself will not be a paper, it will be a book. That I agree, this is there.
My question is regarding can you give us some insights on the use of reliability and survival analysis, current research interests in medical research?
In medical research?
Yes.
In medical research, eventually what we use as reliability, it is not called reliability there, it is called survival analysis. And people start from clinical trials, because if you are using this in medical science, you must know what is clinical trials. Starting from clinical trials, have you gone through any survival analysis course or anything?
Yes. So, I mean, I just want to know the current, research interest in survival analysis in that way.
Current interest actually is not that way specific, because there are lots of open problems in your medical science as far as survival analysis is concerned. Because in survival analysis, mostly we use two estimators most of the times. Nensol-Allen estimator, and another is Kaplan-Meier estimator. Okay. And eventually both have some drawbacks. Can we find some really good estimator where it has nice properties, it can really give some physical significance, but mathematically it should be challenging in the sense that whatever problem we want to solve, that will be solved through that. All those things, if you can answer, that would be a really good thing.
One more thing that I want to add, that is, in survival analysis, mostly what we have seen that mainly they wants to define the hazard function, and based on the hazard function, they try to define.
No, it is not correct. It is not correct. Hazard function is one way of defining. This is just one way. I can tell you a couple of more. First, actually, people started from your survival function. Then from survival function has a drawback in the sense that survival function, if you tell, this is eventually the two survival curve you are drawing, and you try to see whether one is dominated by the other. If there is a crossing, what will happen? There is no answer to that. And that's why eventually we try to see each and every point, what is the hazard rate, the failure rate, instantaneous failure rate at every point. Okay. That's why actually hazard rate came into picture. And hazard rate sometimes becomes too stringent. Then there is what we may not be interested in what is happening at each and every point. We may be interested like this. Suppose I have some used item. I think when I wrote this couple of issues, there actually was, for example, it's cumulative, what I call cumulative residual entropy. What is that? That eventually is the entropy of some system which has survived for some t units of time. It is exactly that, because your density function is replaced by f bar t. Okay, f bar t, and of course it is being replaced by your survival function of x minus t given that x greater than t. That means this unit has survived up to t units of time. What is the remaining life of that? Okay. Once it has survived from t units of time, we may be interested to know how many life it is remaining. Right? That may be of some interest, because I have two things. For example, it mostly happens in US. I have gone to the shop and I want to buy some used product. Okay. And in used product, I might be interested to know it has survived from some unit of time. That's fantastic. I might be interested to know the day I buy, after that, which one will survive more. That is eventually what is called mean residual life. So based on the mean residual life, a lot of literature is there, and this is used in survival analysis. So failure rate is not the only thing. A lot of other things are used.